Hey everyone, this is Jacob from RoboFlow. I'm here today with Matt from RoboFlow to talk about an intro to computer vision. Matt, tell us a little bit about yourself, and then we can kind of dive into the topic at hand.
Yeah, well, thank you for having me on. This is my first time doing a fireside chat with you, and I'm excited to do it. I've watched a couple of them before. I'm RoboFlow's new hire. I'm our growth manager, so working on a lot of different problems throughout RoboFlow, and just getting to work with you, Jacob, and the rest of the team. So it's been a busy 6 weeks so far, but I'm very excited to be here.
Awesome, awesome. So Matt put together a really awesome post recently about an intro to computer vision, which I think a lot of you would be interested in kind of hearing about. So we're here today to kind of take it apart and have a discussion about computer vision, just kind of from a high level. And so let's go ahead and dive right in. So Matt, what would you say, just kind of at a high level, is what is computer vision?
Yeah, so I like to think about computer vision as it's getting a computer to see and understand the way you and I as humans see and understand things. So it's, our goal is to just teach a computer how to do something, so that, for example, I have my coffee mug here. It is in the early morning for me here in Baltimore. And by early morning, I mean 11:30 a.m., but I drink coffee at all hours. Our goal is to be able to teach a computer to recognize that this is a coffee mug. And ideally, at some point, you can teach computers to do all sorts of things with it. For example, if there was a robot, if that robot needed to pick up this coffee mug and wanted to take a drink from it, that robot or that computer would need to be able to recognize, this is a coffee mug. Where is the handle? How do you move the arm? Again, if it's a robot, it might have like a bionic arm or something to grasp the handle, pick it up, and then move it to your face. These are all things that we as humans do, but we don't really think about it beyond when we're babies and children, because it just becomes so natural. But for computers, we have to teach them to do all of these things. So computer vision, the way that I think about it is, it's the way for computers to be able to see and understand things the way that you and I do as humans, even though you and I as humans do it really implicitly and just kind of naturally at this point.
Yeah, definitely. So how would a computer kind of like even start at, kind of being able to identify things and that it's being shown?
Yeah, so that's a good question. And I think that one of the things that's helpful is to talk a little bit about my background. So before coming to RoboFlow, I was a data scientist and an educator. And so when we think about data science, there's a lot of different kind of things that we often think about. But the goal is for us to be able to give data to a computer and for that computer to pick up patterns. Now, this is a very, very oversimplified version of what a data scientist does, but the human is involved with it. It's not just the computer picking up on patterns. There's a lot of human creativity that has to be involved in data science. But at the end of the day, when we think about the types of models that we want to build or the types of things we want computers to be able to do, we as humans take data or information, we give it to the computer, and the computer uses that to learn or to get a better understanding about the world around it. So computers can actually do the same thing with images. And I think we've got a visual that we want to show that kind of will hopefully help to make clear how computer vision is very much like that just general idea of data science. So what you see on your screen here, these are actually three versions of the same picture of Abraham Lincoln. So all the way on the left-hand side, you've got this very, very pixelated picture of Abraham Lincoln. And you might be able to make out like the boundary of his head, where his eyes would be. You may be able to tell that he's got the big black beard that you generally think of with when you think of Abraham Lincoln. So you see that image on the left. Well, if you move over to the middle image, it's that exact same image, but you'll notice there are numbers in each of those pixels. That number represents how light or how dark that pixel is. So for example, the darkest pixels around the beard area, you'll notice that those have very low values like 0 and 1 and 2. Conversely, the lightest pixels, like around his forehead, are in the 200s. You see like 237, 239, 251. So those numbers represent how light or how dark a pixel is. If you move to that image all the way on the right, you see the same exact thing, but now we've just dropped the color itself. You don't see any of the grayscale. All you're seeing is the numbers, but those are the exact same numbers. All three of these things are representations of the same image of Abraham Lincoln. Now, the computer can understand those pixel values on the right-hand side in that image. That's something that we feed into a computer and get it to learn and understand patterns. Where do the dark pixels or those low numbers tend to cluster? Where do the lighter pixels and where do the higher numbers tend to cluster or appear in these images? And computers can pick up patterns in this way, just like if you were to give a spreadsheet of data or a pandas data frame or an R data frame of information and send that to the computer, computers will be able to learn about how to see and understand what it is looking at here in a similar way to what you would do if you wanted to get a computer to give you a line of best fit for some data or build a decision tree or random forest on some of your data as well. So this is sort of how, if we pull the veil back a little bit, how computers start to understand how to see in a way that you and I as humans also get to see.
Mm-hmm. Yeah, definitely. That makes a lot of sense. I think this one is particularly fascinating, that there's only like 10 or 10 by 10 pixels or something, and we can still already kind of pick up that this is Abe Lincoln, and this is all the data that you would need to send into the computer to kind of get it to start to learn some of those basic concepts that we just kind of take for granted.
Yeah. And luckily, in this case, I told you that it was Abraham Lincoln. So if you had, might be harder to pick up on that. But when it comes to a computer and a computer learning about this, maybe we show the computer, let's say that we wanted to have a presidential detector or a presidential classifier. And we wanted the computer to be able to understand, am I looking at a picture of Abraham Lincoln or Franklin Delano Roosevelt or George Washington, three different American presidents throughout history. And what we might do is we might take a bunch of images, whether it's 5 or whether it's 500 images of Abraham Lincoln, of George Washington, of Franklin Delano Roosevelt or FDR, and pass all of those into the computer. And it sees on the right-hand side that array of pixels that represent the colors that are shown in the image. And eventually, what will happen is that the computer will be able to pick up on those patterns. Again, we oftentimes think of Abe Lincoln with a beard. However, to my knowledge, George Washington did not have a beard or was not known for having a beard. And frankly, I could not tell you about Franklin Delano Roosevelt if FDR had a beard or didn't have a beard. But the computer, by looking at a bunch of different pictures or these pixel values of Abe Lincoln versus George Washington versus FDR, may ultimately get to understand when it sees a bunch of those low pixel values in the bottom part of the image, that might mean there's a beard there, which is indicative of Abraham Lincoln. So in any case, yeah, it's really exciting to see how computers can start to learn about images, because it's frankly really, really interesting and really exciting. And we can go far beyond presidential detectors or presidential classifiers. And instead we can solve a bunch of different problems with computer vision. So yeah, this is just one of many, many, many examples.
Certainly. So yeah, so kind of thinking about different examples, from what I've gathered, there's a few kind of archetypes of computer vision problems that the different things you can be trying to do will fall into. And was kind of wondering if you could take us through some of those and kind of break down the different branches of computer vision, if you will.
Yeah. So the first thing that I want to say is that computer vision is a very, very, very fast growing field. There are so many different organizations who are doing research in computer vision. Like I said, there are many different applications. And so the applications that we talk about here are not going to be exhaustive of, or the types of computer vision problems won't be exhaustive of all the types of problems that one can solve. And as time goes on, right now it's at the end of 2020, but in who knows what will happen in 2021. I know that you've written a few blog posts this year about, or rather more than a few blog posts this year about which models are the state of the art models, and how it's like every 2 months, there's a new model that tends to outperform old models. And it's really exciting to be part of that and to see how quickly that stuff is changing. So just wanted to add that caveat up front that with the what we're going to go through here in a minute, this represents what the landscape of computer vision looks like today in December of 2020. But when we think about January of 2021 or December of 2021 and beyond, it may look very different. So with all of that being said, yeah, there are 4 very common types of computer vision problems. The first one, and you can see on the left-hand side of the screen, is called classification. So in that image there's a cat. So let's say that you are a person and you want to, like, let's say that you're a child and your parents are trying to teach you what a cat looks like and what a dog looks like. Well, maybe there are, you as a child, maybe there are a bunch of different pictures of cats and dogs. More realistically, maybe your parents would read you a book or something like that, where, you know, they point out what the cat looks like in the book and they point out what the dog looks like in the book. And over time, you see enough images to where you understand this is a cat or this is a dog. The same thing happens with computer vision. So what we could do is we could take a stack of 100 images and we could have maybe 50 cats and 50 dogs. And we feed those into the computer, and the computer starts to understand what differentiates a cat from a dog. What are the features about a cat? Perhaps sharper ears, or more pronounced whiskers, or maybe longer and more flexible tails. Whereas dogs, also 4-legged creatures, they have different features as well. And the computer ultimately gets to pick up on that. That would be considered a classification problem, where in every image, things are put into one of a specific number of buckets. In this case, one of 2 buckets, one for cat and one for dog. You can think of it as like categorizing flashcards. Each one goes into one pile or another pile. The example of the presidential classifier that I mentioned would be an example of a classification problem, because there you've got images of Abraham Lincoln, George Washington, and FDR. In each image, you only have one of those presidents. A closely related problem is called classification and localization. It's got the same sort of approach where you try and classify which bucket an image falls in. But what you'll notice about the image here is there's a square around that cat. And that's what's called localization. Not only are you trying to predict in which bucket does an image fall, but you're also trying to localize in that image or identify what location in that image the cat falls or the dog falls. There's a lot of examples of this. And so before moving on to talking about object detection and semantic segmentation, a real world example of this is like a wildfire detector. And actually somebody's been using RoboFlow to tackle that. So
oh, yeah.
So sorry, I guess we'll move ahead a little bit here. Yeah. So this would be an example of a classification and localization problem. So in this image, this is an open source data set. You're able to play around with it. What you want to be able to do is the user here wants to be able to identify when smoke happens and where that smoke happens, so that a drone could be dispatched to try and dump water on the source of that smoke to prevent wildfires from happening. So this is an example, like I said, of a classification and localization problem. Not only are we understanding, is there smoke or is there not smoke in this wildfire detector or in this smoke detector, but we're also trying to localize where is that smoke. And so you can see the light green box or the yellow box around that image or around the wildfire smoke specifically saying, yes, this is smoke. One other thing that I want to call out for people who may or may not be familiar with this, you'll notice that there's a percentage there as well, like smoke 98%, smoke 94%. This is you might think of this as the confidence or the probability that it actually is seeing smoke there. Computer vision is not perfect, just like human vision is not perfect. And so whenever we make predictions, we're often able to say, hey, we're pretty sure that this is smoke, but there's a possibility that it's something else. Maybe it's really foggy out, or there's a low cloud, or something else going on that makes it look like smoke. But as we see here, there's a pretty high chance that what it's looking at is smoke. And we as humans look at that and probably would believe that it's smoke too.
Definitely, definitely. I mean, this use case really just shows just how useful this can be. I mean, I couldn't imagine if every mountaintop in California had one of these. It would be, all kinds of fires could be prevented with this kind of surveillance.
Right. Definitely a lot of potential to applying computer vision in this and many other contexts.
Definitely. But yeah, so I guess kind of to carry the conversation forward, I guess I'm just kind of curious, now that we've kind of seen all the cool things that computer vision can do, how would one kind of like get started on sort of like actually starting a project and getting going, and what might it look like to get going in computer vision?
Yeah, so for people who come from a data science background, the steps to tackling a computer vision problem are not going to look that different from the steps of tackling just a general data science problem. In this case, data are going to be the images that we work with. But if you're less familiar with a data science workflow, for example, if you are a web developer or you're a product manager or you're somebody who just doesn't have as much experience in data science or data analysis, there are a series of steps that you can take to be able to produce a computer, or rather solve a computer vision problem. So this is something that we've put together at RoboFlow, and you'll notice that there are 7 steps to this process. Moving from left to right, you have collect, label, organize, process, train, deploy, display. Now I write about all of these in the in the article that's posted on the RoboFlow blog. But the idea here is that you start on the left-hand side with collecting data. You have to, for example, with that wildfire detector, you need to be able to go ahead and you need to be able to have images of both wildfires and non-wildfires. Then moving into the labeling stage, somebody would have to label the images. So when you saw, for example, the wildfire, there was the smoke, there was a big green box around the smoke. That box is what we call a bounding box. And in order for us to be able to use a bounding box, or rather, in order for the computer to be able to put a bounding box around that smoke, the computer has to be told what is smoke and what isn't smoke, and what do other bounding boxes look like. So you, as the user, will actually have to annotate or label your images by drawing a bounding box around objects. That's something that, as you see here, there's a couple of integrations. You can use a tool called CVAT or CVAT. You can use Microsoft VOTT. We actually just last week, we publicly launched RoboFlow Annotate, where if you upload images to RoboFlow, you can actually annotate those images directly in RoboFlow as well. So you can put the bounding boxes around images. Everybody can do it. That's free. And honestly, I find it kind of fun. So I would encourage you to upload a couple of images and try that out. Once you've got that done, then what you need to do is you need to move into organizing and processing your images. So oftentimes when you're tackling a real computer vision problem, you're probably working with a team. So maybe you and a couple of other teammates are collecting different images and labeling them. You need some place to organize all of that together. And then you need to process those images. So let's say that, for example, I have an iPhone, but let's say that Jacob, you have an Android phone, and you and I are both taking images of, if we go back to like the cat and dog classifier, maybe I take a bunch of pictures of my dog. I don't know if you have a dog or a cat, but maybe you take pictures of a pet. Well, our pictures or our images are probably going to be different sizes because an iPhone camera and an Android camera are probably not going to be the same. And if somebody else has a digital camera or whatever, there's all sorts of reasons why images may come in different shapes and sizes. Well, that's not good when it comes to solving a computer vision problem. That actually presents a number of challenges. So you need to format your images and pre-process them to make sure that they're all the same size. You can also do something really, really cool called image augmentation. But I want to pause before getting into that because I think that's really cool. And I think there's a lot of stuff that can go into that. So I just want to see, is there any questions that you have about kind of the first, I'll call it 3.5 steps that we've talked about for this process so far?
Yeah, I have a few, but maybe we keep going along, and then I'll ask you some deeper dives on individual sections once we've seen the whole all the way through to the touchdown line.
Sure. So when it comes to, so once you've pre-processed your images, you can also do something called augmenting your images. One of the biggest challenges in all of data science or in all of statistics, if you've ever taken a statistics class, it's kind of drilled into your head how important it is for you to have as large a sample size as possible. Now, there are a couple of cases in which you don't want to do that, or you have to be very careful about how you do that. But all else held equal, the more data you have, the better. And that probably makes sense. If we think back to that presidential detector, that presidential classifier, and we're looking at Abe Lincoln, we're looking at George Washington, and we're looking at FDR, I think that if a computer has 5 images of each versus 500 images of each, the computer is probably going to have a better or an easier time generating predictions that are accurate when you're working with 500 images in each bucket. Because if you only have 5 pictures of each, well, that might not be enough for the computer to learn. Same sort of thing with a child who's learning what's the difference between a dog and a cat. The more times a child sees a cat and sees a dog, it's easier for that child to understand this is a cat versus this is a dog. So image augmentation is this really cool technique where when it comes to image data, we can make small tweaks or small perturbations to the data that will allow you to increase your sample size. So for example, what we've got here is we've got the RoboFlow mascot, Lenny the raccoon. And so if we look at the image all the way on the left, you have Lenny, and there's been a bounding box drawn around Lenny. Well, there are a number of changes that we can make to this image. Obviously, this is a picture of Lenny, the raccoon, and it should be treated as such. What we can do, though, is if you look, so you've got that left-hand image, moving over to the right a little bit, you'll see 2 copies of that same image. I'll actually start with the one on the bottom. So notice that the one on the bottom is the exact same picture of Lenny, except it's a little bit lighter and it's been cropped a little bit. You'll notice that his paws are actually at the very, very bottom of the image. If you look at the image directly above that, you're going to see a similar image of Lenny. But again, there's some visual effects that have changed. You'll also notice that that picture has been reflected so that Lenny, it's still Lenny, it's still a raccoon, but it is you're seeing slightly different perspectives of Lenny. You can move on to the right and you can see the same sort of thing. You can see the image tweak we apply a little bit of shear to it, or we apply a little bit of rotation to it. We blur the image. We might rotate it 90 degrees. We might add a bit of noise to it. All of these things are the same picture of Lenny. So let's say that we took one picture of Lenny. We've now used image augmentations to go from one image of Lenny to 6 images of Lenny. Now, I do want to add a caveat here. This isn't some magical solution. This is not something where we can just say, hey, we've got, like, we had one picture of Lenny, now we have 6 pictures of Lenny, and so our sample size effectively is 6. These are all very related or correlated images to one another. It would be better for us if we had 6 pictures of different raccoons as opposed to one picture of the same raccoon tweaked 6 different ways. But we're working with what we've got. So you can use image augmentation to increase that sample size that's in your data. And what this does is it gets your computer to understand a little bit more about, in this case, how do you identify a raccoon in the woods? So by changing the lighting a bit or changing the angle or adding a little bit of noise, the computer can start to understand specifically what is it that makes a raccoon and how can we better detect that? So I think image augmentation is one of the coolest things, and it's fairly unique in my experience to things like image and video computer vision problems.
Yeah, definitely a super powerful way to be able to, expand your training set and really kind of show the computer as many different versions of things as you can. That's really amazing. Yeah. So moving along on the full process. So let's see. Let's step back for a second. So we've gathered a bunch of images. We've annotated them with labels. So we have things that we can teach the computer. Now we've got this data set. We've made it a lot bigger and more diverse with augmentations, and we've used pre-processing to get it into the right format. So where are we headed?
Yeah. So if we step totally back, remember our goal is to be able to do a computer vision problem. We want to teach our computer to see and understand things the way that you and I do. So we've kind of done all of the input stuff. Now we're at like the building phase. This is where we train a model. So depends on if you come from like a data science or a more technical background or not, but I'm going to flash this image up. It's going to look really scary, but we'll talk about it. So we want to be able to build a model. Now, a model is just a simplification of reality. So you and I build models all the time, every day. So back before the COVID times, when people generally would actually commute into work, we all had mental models about how long it takes us to commute to work. For example, I live in Baltimore, and my fiance would go to work every day. He works in Washington, D.C. That is a 90-minute commute. Now, every single day, his commute was not exactly 90 minutes. In fact, it was probably never exactly 90 minutes to get into the office, but you've got this mental model. It takes 10 minutes to get to the train. It takes 50 minutes on the train. Then you go through the Union Station, you get on the metro, you walk to the office. Like, you've got all of those steps, and it's roughly 90 minutes. It's not a perfect model, but it helps us to understand what are the things that we need to do. For example, my fiance can use that to figure out when does he need to be in the office? When is the last train he can take to get into the office on time? When does he need to set his alarm and things like that? The model doesn't have to be perfect, but that is all a model is. So what we're seeing here is a much, much, much more sophisticated model. When it comes to developing computer vision models, there are a number of choices that you can make. By and large, the most impressive types of models are things called convolutional neural networks. And so if you're familiar with convolutional neural networks or had experience with them, that's great. I'm not going to walk through each of these components because, frankly, it's when it comes to an intro to computer vision, that's not really worth our time here. But the goal is for us to be able to take an image and turn it into a prediction. So if you look in the top left corner where you see it says backbone and there's like C1 through C5, at the very bottom of C1, you see the outline of an image. That is one image. You can think of that as an image of Lenny the raccoon, or an image of Abraham Lincoln, or an image of a cat or a dog. And what it's going to do is it's going to go in this really complex looking system of pipes here that will then move from left all the way to the right. And once you go through all of these numeric transformations and frankly, just all of this math that happens, at the end, the computer is going to be able to learn what is this image, or the computer is going to be able to make a prediction about what this image is. What we do and how we train a model is we give our model, or we give our computer, a lot of training data. So we might, if we wanted to build a Lenny the raccoon object detector, which we didn't talk about object detection earlier. It's where in an image, you may have multiple objects and the computer should be able to pick up Lenny or pick up any objects in the image that you want it to pick up. So what you do is you might give your computer 10 or 100 or 1,000 or 10,000 or a million images of Lenny with bounding boxes drawn around Lenny. And what is going to happen is we're going to pass those images into this network, and it's going to move all the way from left to right. And then at the end, it's going to check and see, was I correct or was I not? It's almost like flashcards. You look at a flashcard, you make a guess as to what the answer is, you flip the card over, you see whether your answer was right or not, and then you use that to adjust your thinking. And you do that over and over and over again. That's the way this convolutional neural network is going to work. Images are going to be passed in. The computer is going to make a guess. It's going to look at the true answer and say, oh, I was really close, or I was not very close. If you were really close, and that means your computer is doing a good job. If it's not very close, the computer says, we've got to adjust a lot of things. So let's adjust. Now let's move the next images through the network and see how it goes again and again and again. So that's the way that machine learning models in general work. Convolutional neural networks are especially complex models, but they tend to do pretty well with computer vision. And I know that you, Jacob, do a lot of work with the different types of models that are out there, like the efficient det and the scaled YOLO v4 tiny and YOLO v5 and all of that. So I kind of want to toss it to you because this really is your bread and butter.
Yeah, this is really a personal passion for me. But I agree with Matt that some of the details are kind of outside of the scope of this just intro to computer vision. But the important thing is kind of how Matt outlined, that there's a bunch of images coming through. There's a network that's being trained. And then at the end, you're able to get kind of the prediction out. So you're able to, it's really just a data transformation process of transforming the image that's coming in into some kind of actionable insights. And then I guess kind of, nearing the end of our talk here, it's been, it is quite a process to kind of go through to make sure that you're kind of getting everything right throughout this pipeline. But I was kind of thinking, Matt, maybe we talk a little bit about what the motivation is for this process and trying to keep everything well connected throughout the way, and what might be sort of the motivation behind all this work.
Yeah, so the motivation behind all of this work is to do what it is that you want to do. You're trying to teach a computer to see for some purpose. So let's figure out what is that purpose, and let's get the computer to do that, not lose sight of that goal. So for example, if you want to be able to build an app that can an app that can be deployed to your phone and can, you download the app and you pull it up, and then you're able to maybe scan something, like you're able to scan a dog and see what kind of breed it is, or you want to be able to scan, a bunch of things in a factory very, very quickly and efficiently so that humans don't have to look at everything. There are literally an uncountably infinite number of things that can be done with computer vision. So really the sky's the limit in terms of the thing that you want to do. Once you've gone through all of these steps, then you get to decide how you want to use that model. Do you deploy that model to an app, like I just said? Do you build that model and kind of share that model with somebody else so that they can use it? Do you want to be able to deploy it on a website so that you could just do with a video camera? There could be like a bounding box that you put around something. There's all sorts of different things that you could do there, and you can display your results. But that's the end goal. To a related question that you asked is, let's talk about all of those pieces and having a unified approach to all of those pieces up front. There's an adage in data science and in many other fields that we describe as garbage in, garbage out. So the idea is that if you put garbage in, whatever you get out of it is going to be garbage. So for example, let's say that I wanted to work on, let's say that I wanted to be able to look at a customer satisfaction. Let's say that I work for a company and I want to be able to understand how satisfied people are with my service. So what I do is I collect data, and let's say I do everything right. I build the exactly correct type of model. Any statistical assumptions that are made are satisfied. I've got a ton of data. I cleaned the data well that preserves the original form of the data. Like, I didn't make any mistakes. I handled missing data, did all of the things from start to finish correct. But let me tell you, I gathered my data from Yelp. What do you think, Jacob, is the problem if I gather my data from Yelp that I'm using to understand customer satisfaction with my product or my service?
Yeah, I mean, it might be a total mess. You might be getting, all kinds of different data that may not be accurate. I'm not entirely sure, but
Yeah.
um,
And when we think about Yelp as a service and what, you think about people using Yelp online, Yelp is not really a random sample of your customers. Yelp is generally where people go to complain. Now, that's not always the case. Some people are just really, really big Yelpers. They'll go on Yelp and they'll review people and review services and products and things like that constantly. There are some people who might say, hey, I had a fantastic time and I'm going to go on Yelp and I'm going to give this 5 stars. But in a lot of cases, just based on what I've seen on Yelp, most frequently people go to Yelp because they're complaining. They have something to complain about. So if you wanted to understand how pleased are people with my business, with my organization, and you go on Yelp, that's probably going to be a pretty skewed view as to how people actually feel about your service. The same sort of thing is happening here. So what you see on your screen, again, you might think of it as like a garbage in, garbage out. So what we see on the screen here, this is considered an object detection problem. You'll notice that there are bounding boxes around many different objects. So you've got cars that are labeled, you have motorbikes that are labeled, you have people that are labeled as person, you have buses. It looks like those are all of the individual classes that we have here. Now, this model does an okay job because you see, for example, there are a lot of bounding boxes, and the bounding boxes seem to be pretty tight around the objects themselves. The bounding box for a car pretty well matches the limits of the car. It's certainly not perfect, but it seems to, those seem to be okay. The problem with this is that when you look at this image here, there's a lot of things that aren't labeled. There's a lot of things that are missing. And so that might indicate, if you build your model and you take a look at it and you say, this is what my output looks like, you're not done with your process. You need to go back and see what are certain choices that I made that prevented my model from being as accurate as it could be. Is it that I made the choice to build my model without enough data? Do I need to go back and collect more data? Do I need to augment my images more? Did I do a poor job of labeling my images? Do I need to be better about drawing bounding boxes very intentionally around each of the objects? Did I just not have enough data on motorbikes, for example? I see a lot of motorbikes in this image that are unlabeled. So once you go back through your process and focus on that data collection, that data organization, that pre-processing and augmentation, then what you might do is retrain your network, and then you end up with a significantly better model, something that looks like this. So you'll notice that it's still not perfect. There's a lot of things at the very, very back of the street, in the back of the image, where you see cars and things like that, but the computer isn't picking up on those. You'll also see some people on the other side of the road, some people in motorbikes that are missing, but you'll notice that the computer is doing a much better job of identifying things that are directly within its field of vision here in front, especially that little cluster of people in front of the bus, where on the last image, you saw a lot of that was blank. The computer is now picking up these people, these motorbikes, and that's a good thing. So we would say this model is performing better than it was in the previous image.
Definitely, definitely. And I think that that is, just a really good example of the motivation behind the whole process, which is just to not only build a model that will do the job that you set out for it to do, but that it will do it well with high fidelity.
Yeah.
And then yeah, and then just reflecting a little further, the beauty of things here is that once you get this model finished, um, and you get it to a place where you want it, you can obviously continuously improve it and make it better and better. But then you have something that you have locked in place that can make inferences, as many times as you want, and it will run, just like a computer, it always runs. So that's a really motivating fact, I think.
Yeah, and I think it'd be remiss if I didn't bring up the idea of ethics and of equity when it relates to this, because this is a really important point to bring up. As we think about like the two images that we saw there, where there was the image that didn't perform as well, and there were a lot of annotations that were missing, and then the latter image where things look to be performing much better. It's important to keep in mind what your goal is, and it's important to keep in mind what is the problem that you are trying to solve. For example, if you're thinking about a presidential classifier, the FDR, the Abe Lincoln, the George Washington example, that is, that's probably, I don't know what the use case for that would be, but I imagine that's fairly low stakes. That might be a toy project. That is something where if your model got a classification wrong, then that probably wouldn't be the end of the world. There might not be a ton of harm that's associated with your model getting that wrong. In the case where we were looking at that street, think about that in the context of self-driving vehicles. And that is one example where obviously you need a model that is performing very, very, very well if that is the goal. And so keeping that goal in mind, having a self-driving vehicle, for example, there are a lot of ethical implications and equity-based implications that are wrapped up in that. And so we need to be cautious to not say, well, it's good enough for our purposes. Well, we've got 95% accuracy or 99% accuracy. People will often say, like, would you ever get on a plane if that pilot had a 99% success rate or something like that? And I think that a lot of people would say no. And so it's very, very important to think about that, as well as there are a lot of documented examples where, especially as it relates to computer vision for people, that based on a number of different factors, there are models tend to not perform as well for people of color or people with darker skin. And a lot of that has to go back to the beginning of the process. Are we collecting enough data from various groups of people? For example, if your training set for data, if you're doing medical imaging and the training set for your data is overwhelmingly white patients, that affects the performance of that machine learning model. If you're trying to build a sensor that can detect like the hand sanitizer sensor, you put your hand underneath and it detects and it shoots that out. If it's generally tested in environments that are lit, that better augments or better calls out white skin than darker skin, darker pigmented skin, then that technology may not perform as well for people of color. And so I think that it's really important to understand how none of these pieces are like intractable from one another. And so that all boils into, when we think about building these types of models and just the iterative nature of it. If you go back to Jacob, if you go back to that slide where we were talking about like collect, label, organize, and all of that, the goal is to be able to design things in a way where you see from start to finish, you go all the way from left to right. You start with collect, then you move into label, then organize, and all of that. And that makes it easy for us to mentally digest. But realistically, there's a lot of continuous improvement that's got to take place. There's a lot of opportunity for us to, once we train that model, say, hey, that model is not performing as well as we want. So before we deploy it, let's go back to the collection phase and get more data, or let's go back and relabel and improve the labeling on that. So I know that was long-winded, but I think I definitely would have been remiss if I hadn't brought that up. And it's something that absolutely needs to be considered when tackling computer vision problems.
Most certainly, most certainly. And as Matt pointed out here, this whole continuous loop process is something we're we're working heavily on making easier and faster at RoboFlow. So if you're thinking about using computer vision, consider checking us out. And, I just wanted to say, thanks so much for joining Matt and I today in this discussion. And, it's been really awesome. So
Yeah, thank you. I'm excited to do more of these fireside chats in the future and perhaps lead a few of my own. But yeah, excited to be here, excited to be working with you. And I'm looking forward to hearing from people who view this video and understanding what are the types of problems that you're solving with RoboFlow.
yes, definitely, definitely. So thanks so much for joining us, and we'll see you all on the next video.
Take care.